Okay, I think we can start officially. Welcome back, everyone. So we're doing our third exam review for our third exam, and that means we're pretty much done with the course at this point. There's still some interesting topics that we have to complete that are going to take some time to get through, but if we look ahead in the schedule on the Moodle website, after exam 3, we'll be working on section 10.5. Then after that, there's just 3 more sections, 12.1, 12.2, 12.3 to finish out. We'll be completing them these weeks here, taking us to the finals week. So we'll be in really great pace to complete our topics and have some good review days for our upcoming final exam. So our final exam is scheduled to be on Monday. I will put the time in here really soon. I believe it's about the same time as our class, but I'll make that specific. Usually what happens is the university scheduler emails everyone, Michael Tim, right around the time of Thanksgiving break. And then once I get that official information, I'll put it down here so we can all plan a little bit better. Also, once we get through next week, we'll be on our way to the Thanksgiving holiday. We won't have classes at all that entire week, no classes or office hours, but I'm still available by email. So if you have questions, if you're requesting extensions on due dates, if you're working on the holiday, then I'm sorry, but I'll still be there to help you out. So that's where we're at so far. We're going to go back to exercise 2 in the review problems. There's still 3 of them to go. If we run out of problems, we'll just go down to this document. There's many more review problems in there that we could take a look at. And if you have a question that you would like to see, maybe you saw a fun problem here, please let me know. Maybe right away after we finish the next exercise, anything like that. And I'd be happy to change gears and take a look at a different problem. Well, the reminder is the thing that we typically do right before an exam is I always release a quiz, and sometimes those quiz topics seem a little bit strange. Like this one here is just a redo of a confidence interval. The reason I did that this time is it just made sense. If we have an exam 3 coming up involving confidence intervals, we might as well do a confidence interval quiz. So here's a redo on that one. If you solve it early, then I will grade it as soon as possible. If you emailed it to me, I'll email your graded solution back. If you send me a hard copy, I'll scan it and send it right back to you. So if you want feedback on your 12th quiz before the 3rd exam comes up, get it completed early, and I'll let you know how you're doing on that so you can use that as another way to study for the exam. Well, any questions at all, folks, with those announcements? Okay, well, let's get back to our exam 3 review problems on exercise 2, it says we're at. So here we are. This one looks like a pretty heavy looking study. It says prothrombotic factors in children with stroke or porencephaly. I'm not sure if I'm saying that right. Porencephaly, something like that. I believe it has to do with our head here. This is from the Pediatrics Journal. I'm not sure the date on this one. And what they've done is it says they compare differences and similarities in children with arterial ischemic stroke and porencephaly. So a bad condition is what they're taking a look at. They tell us next, there's 3 classification categories were used. There was perinatal stroke, delayed perinatal stroke, and childhood stroke. Then they go on to give us numbers saying of 59 children, 25 were diagnosed with delayed perinatal stroke. So that's the whole problem. It's asking us to describe a parameter, calculate sample proportion of successes. So here we're just doing a confidence interval about these data. But before we get too far, we should reread this again. Let's take a look. It says there's 3 classification categories used. That's a bit of a concern because our confidence interval is for categorical data with 2 categories. So if we see 3 categories, it almost feels like it doesn't fit. But we're in good shape because they tell us right here, 25 of the children were diagnosed with delayed perinatal stroke. It looks like that's the category we're interested in the most. So the other 2 categories are going to be considered failures. This category is going to be considered the success, the thing that we're actually interested in. Let's start this time by saying a success. Definitely I want to put quotes on it this time. A success is getting the outcome that we're interested in, which is this time having delayed perinatal, I should have practiced those words before coming to class today, stroke. So we have a notion of successes. We can say that there is 25 successes, and the sample size is n equals 59 of the children that were in the study. We're not too sure how they got those children. There's no information about randomization that they gave us. But so far, we can at least start this procedure and describe a parameter. Any questions first, folks, with the context on this one? Okay, definitely kind of a weird problem. And really this first word right here, let's see if we can just look up some of this, because these kinds of medical question problems, they're pretty interesting, but they can also be massively confusing if we're not too sure what the terms mean. Let's see if we can look up just one of these. Let's search prothrombotic, and it says, oh boy, just more medical terms. It looks like they're talking about blood clots if we're reading this, which makes sense if they're talking about strokes. So something to do with that kind of information. So we could look into this more and more and more, especially if you're interested in this problem. But for the purpose of getting through the problem, just being at least somewhat familiar is a good idea. So now we can describe the parameter P. We can say that P is going to be the proportion. It's describing a population, so we can say proportion of all children. Now let's take another look at this. Children with stroke or porencephaly. It says here we're looking at children with arterial ischemic stroke and porencephaly. 3 classifications were used. So it looks like we're talking about all children with that specific condition. Let's see if we can paraphrase that. That's a heavy thing to write out. Let's say proportion of all children with these conditions that have delayed perinatal stroke. We would definitely want to get that portion in from the context, because that's what the success is describing. I put here, just to simplify writing out the parameter, these children is referring now to children with the condition right here. So that's definitely baked into the context throughout. So if we say these children, we'll be referring to those children with that specific condition. So that's our parameter so far. Any questions or additions that folks would want to put here, other than let me spell stroke correctly? Okay, well, if we have our parameter, this is the thing that we're going to be estimating. And that makes part B exciting, because part B is an estimate. It's a point estimate already. Part B is asking us for the sample proportion of successes. Whenever you read this, think P hat. So the hat there tells us we're trying to estimate the unknown population characteristic here. All we have to do is take the 25 successes indicated up above, divide by the sample size of 59 children, and we could leave it just like that. I think we did that once in chapter 10, but if it's indicating to round, then we might as well just round this thing. So now 25/59 taken to 4 decimal places, we'll have a 0.4237. So as it stands, we can say our best one number estimate of the proportion of these children that are having the delayed perinatal stroke is about 42%. But there's more to the story. There's an error in that estimate. So we're going to quantify it first by using the standard error. Then we'll check conditions and construct a confidence interval. So we're just about through to the next step. On the next step, a lot of these problems are really just turning into, in a certain sense, a vocabulary kind of question. You had to know what a sample proportion represents. The symbol is p hat, but it represents successes over the sample size. And then when you see standard error, we have to know what this represents. There's multiple different standard errors. We'll see a new one in chapter 12. And we already use the standard error in two different ways. It has one format in hypothesis testing, but if you're doing a confidence interval, it will have this format. SC for standard error of p hat just tells us which one. It'll be the square root of our p hat times 1 minus p hat. So that takes care of the numerator, then divide the whole thing by sample size n. At this stage, we're just throwing values inside the square root. So let's grab the 0.4237. 1 minus 0.4237. Then the whole thing is divided by 59 children. So that's what gets thrown into the calculator. And we've mentioned this a lot, but it's always a good for a reminder right before an exam. If this is on your paper, even if you made a mistake on the calculator, you will get a tremendous amount of partial credit by knowing the concept and putting the right information inside. So any kind of stress on the calculator should never count a lot on a timed exam. And that's the way I award partial credit on these kinds of problems. So now back to the calculator, though, we do have to calculate it. Let's see, we can go for the one-stop shop and put in second square root. We're thinking of putting it all in one. Then it's going to be 0.4237. Insert a parenthesis and 1 minus that same value. We close the parenthesis there, then immediately hit division by the 59. And we should all be getting this value next. I've got a 0.0643. Is that looking all right to folks at the moment? Okay, let's insert that into the problem. 0.0643. It said 4 decimal places, so we'll take it as is. Now we'll check conditions. And even if the conditions might not work out, just a small hint on the quiz that we're about to solve, quiz 12, conditions fail on this thing. So that's going to be something interesting on the conditions for that new upcoming quiz. Even if conditions fail, you can still give a practical interpretation of the confidence interval. And one thing, I wouldn't take off points, but if your conditions fail, you interpret that confidence interval, you could say we have so much confidence that the true population of something lies between this value and this value, provided that the conditions were met. If you didn't put that in, I'm not going to take off points because we've only seen that happen once. But that's what we're going to do on any problem where conditions do fail. Yeah, go ahead.
So if the conditions do fail, then this whole process still stays the same.
It does stay the same, yeah. But what would happen is if the conditions fail, the actual confidence interval is no longer very accurate. There's a lot more error inside of it. And when we say a statement of with 95% confidence, the true population something is inside here, that confidence might not be 95%. It might be lower. It might be completely off. So that's what's going to break down if conditions fail. On the quiz, it's really, really borderline. And so if you write a conclusion and just mention that conditions weren't completely successful, so you should take these results with a grain of salt, that would be a good thing to say in that kind of context. Other questions so far? Okay, well, let's take a look at those conditions. Like you mentioned before, I'm not going to worry too much about randomization. Many of the problems we've looked at don't even mention it at all. If you wanted to, you can just, for the sake of making sure you looked at that condition, you can say there is no information about how the sample of 59 children were collected. We hope it was a random sample. Even better, a simple random sample is the gold standard for this. But if you looked into this study, you don't have to. But if you had the free time and you really want to, you might find out it wasn't a random sample. They had a certain set of children and they looked at the demographics, other information about the children, and they might reason it looks like a representative sample. That's one of the things that is a little bit foggy in statistics, doing that kind of work. Our author doesn't go into it too much other than to say, when we look at the formulas, oh, where are the formulas? Oh, that's 9.3 additional exercise. That would make sense. In the formulas, the author says the sample is a random sample from the population of interest. That's what we hope, and we hope it's a simple random sample. Or this happens in real studies. The sample is selected in a way that should result in a representative sample from the population. That's going to require a lot of experts that deal with the specific disease that we're talking about here, a lot of experts in statistics itself to justify if that was really a representative sample at all, that could be regarded as random. That's not something we can really do as outsiders. And so we just try to adjust the question by looking at whatever information they gave us. But then the next step we can take a look at is if the sample size was large enough to be successful. So we'll look at that next. This is the part we will we will assess directly. First, we'll look at the number of successes. Now, this problem just gave us the number of successes as 25, so we don't have to do any formula to calculate it. We'll just cite it. Number of successes equals 25, which is greater than or equal to 10. That's always a strange statement, but that's the benchmark we wanted, so we met that. Number of failures. Well, it ought to be larger, so we're definitely in good shape. I would take as a formula the sample size n minus number of successes, which was 25. So this is 59 minus 25, leaving us with, that ought to be a 34. Also greater than or equal to 10. And trickiest thing about this, though, is once we make these two computations, we still have to make a conclusion. If this exceeded 10 and this exceeded 10, we can then say this shows the sample size is large enough. So we have a large enough sample to run through this procedure, and that's what we'll do next, construct a 95% confidence interval. Any questions at the moment, folks, with the discussion on those conditions?
Kind of a bit random, but will we be finding the Z confidence at all in the test? Finding stuff like 96.
Oh, yeah. It turns out the test is only going to involve the 90%, 95, and then the 99%. I'm glad you mentioned that. And that means if you have this table either memorized, that'd be impressive, or just on your page of notes for the exam, you'll be in great shape. I won't ask you to do this process because we only did it once. It wasn't even in the homework. Other questions about that so far? Okay, again, I'm glad you mentioned that. This is a good opportunity to just take this whole table right here. Let's throw it on the notes as we go to solve this. Okay, so we've got our table ready to go. We want a 95% confidence interval. So already from that table, we can just cite and say, at 95% confidence, Z star is 1.96. Sorry, struggling with my penmanship today. There we go. All we did is look at the row at 95% confidence and grab that critical number directly from there. So that's wonderful. That means this whole process is really pretty fast. We just need practice so we're familiar with it. The whole formula is going to be then p hat plus or minus our critical number Z star multiplying against the standard error SE of p hat. So that's the whole formula. And this is actually a pretty good strategy. If you feel really confident that you have that formula down in your mental chalkboard, then you won't have to necessarily copy it down. But once you copy it down, it just becomes a matter of looking up the value, grabbing it and dropping it into the right location. Having this down as a template or placeholder is a valuable strategy here, especially when you're making a lot of substitutions. So first one is p hat, 0.4237. We're going to add and subtract the next thing, Z star. I mean, that one's right there, so no big deal. Let's throw it in. 1.96 goes in. Then multiply that whole thing by standard error. That's the 0.0643. So once that's all set up, all that's left to do to calculate the confidence interval is throw all that stuff into our calculator. Just trying to find a spot to put that. So we'll put the population characteristic, P, right in the middle. That's the unknown. It's estimated by P hat 0.4237. And that's going to be the direct center of the confidence interval because we're adding the same quantity and subtracting the same quantity from that center. So first we'll get the lower bound. Let's clear all that out. It's going to be a 0.4237. So minus to get the lower bound and 1.96. Open a parentheses and put in 0.0643. And that should be our entire lower bound. It comes out at 0.2983 after rounding to 4. Well, how many were you doing on this one? Yeah, 4 decimal places. Yeah, go ahead.
Are you missing the 3?
Probably, let me take a look. 0.4237. Oh yeah, I definitely did. Thanks for spotting that right at the very end. Let's see if we can get a quick correction. 0.0643. Thanks for spotting that. And then with that correction in, we have the more accurate number, 0.2977 now. Other questions or comments at the moment? Okay, thanks again for spotting that one. So 0.2977. And so already, this is pretty interesting information. When we first wrote down our population characteristic P up here, that's the unknown. It's estimated to be about 42%. But if we never did anything further, we wouldn't have known that it's plausible to be as low as around 30%. That's substantially far away from the center, but it's just as plausible. So that's already pretty valuable for us to do this computation. Now let's take a look at the upper bound and see how much it varies there, probably by a good amount. And the reason we have so much width to our confidence interval is because the sample size just wasn't that large. It's at 59. And that's kind of unfortunate because some of these studies, you can't necessarily even get a large sample size if the conditions that we're looking at, I couldn't really judge, but they seem kind of rare. If they're rare enough, we might have to do a completely different method. There might not be enough children to get a large sample size. But if that's the case, we'll just do the best we can with what we've got. And so let's go for the upper bound. On the calculator, it's very valuable to not try to type it in twice. I messed it up the first time. If you've got it in once, use the up arrow feature, hit enter, and just scroll to the left to turn this one into a plus. Now we have a 0.5497. So again, pretty high on the upper bound as well. Well, that's the full confidence interval. All that's left to do is to give the practical interpretation. Let me get that calculator fixed. Any questions so far, folks, to this stage? Okay, does it feel pretty familiar at this point? Awesome, I'm glad to hear that. It again should kind of feel like doing the 1.5 IQ or rule of thumb. The formula is totally different, but the kinds of things you do are highly, highly similar. So last part, we want a practical interpretation, which means we have to cite the parameter P once again. Let's go up to the top. It's a little bit easier than a hypothesis test for sure, because there's just not as much noise going on. We're just going to say we are estimating this quantity here at 95% confidence, and our estimate range from here to here. So officially, we might say something like this. With 95% confidence, pretty much every interpretation of a confidence interval has to say this part at some place. So with that amount of confidence, we'll go up here and just read it out. The proportion of all children with these conditions, that have delayed perinatal stroke finally we say is between 0.2977, if you'd like it as a proportion, or you could say 29.77%. I'd say proportion here, so I'll just stick with the proportion, is between 0.2977 and 0.5497. We finally did it, folks. That's our full confidence interval in this problem. And you can imagine how valuable this information might be if maybe you're a physician that deals with these conditions. Maybe you're a pediatrician, physician, and if you see these kind of conditions regularly, maybe some kind of specialist, you'd be interested in this number. This would represent like the worst case of what could happen to your caseload of children that have that conditions. Practically 55%, nearing 60 of them could have that condition. Who knows how bad that is, but that's something they were interested in the study, so they're probably pretty interested in that upper bound in this problem. But it's hard to say exactly what's going on unless we're experts ourselves, but that's the kind of nice thing about statistics. If they set up the information for us, we don't necessarily have to know exactly what's going on. We can still run through the problem and give them an analysis. The experts would help us along, defining terms and things like that, and we would support them with this conclusion. What we would never tell them is P between 0.2977, 0.5497, 95% confidence, because then they would not have any idea what we're talking about at that point. Well, let's try the next problem. Any questions at all, folks? First on this one? Okay, well, the next one I think is going to be another normal distribution type of problem. And here's how it goes. It says researchers are interested in the length of a particular type of bone in a population of deer. So riveting stuff, I guess. They measure the bone length in a sample of 200 deer. Let's pause right there. The moment you see the keyword sample of 200 deer, you've got a sample size. So it's absolutely helpful to write that out somewhere in your paper. Giving it the unit of deer would only help with the context, not required. So they had sampled 200 of these deer and find that it follows a normal distribution. That's helpful for us. I guess they have to say that or else it wouldn't be a normal distribution problem. They tell us there's a mean of 25 centimeters. There's nothing wrong with the information in that format, but it's a good idea to use the symbols we're comfortable with. I would write mu equals 25 centimeters just from that information. Standard deviation of 2 centimeters. So that's going to be sigma equals 2 centimeters. Next thing we have here is x every time it occurs. This is going to be equal to the length of that particular bone. They never told us which one it was. Probably a femur or something. That's hard to tell. 25 centimeters. Something, maybe a rib bone or something like that. Whatever it is, x is going to be the length in centimeters of that bone in a deer from that population. Okay, so that's the rundown of the problem. Nice things about normal distribution problems is there's usually not as much context, and they're directly giving up a lot of information. You have to have a mean, you have to have a sigma to start working with this. Any questions at all, folks, then, before we get started on this one? Yeah. I think I did say on the exams, include a graph. I'm going to make that optional because I definitely neglected to put it on here. But I'm glad you mentioned that because, again, if you wrote down something like, let's just say on this one, I'll delete this in a moment. If you wrote down a figure like 9342, and I'm not sure how that number came to be, then I lose all basis to give partial credit. And so even if the instructions don't say to include a graph, I would still encourage you to do so just for the sake of that's an extra way to get partial credit in the problem. Let's say it right here just to help us out on that. Let's say officially for these problems, include, well, that seems like we're yelling. Let's undo caps on this. Include a graph to support computations. Other questions so far? Okay, well, let's give this one a try. It asks us, what is the probability that a randomly selected bone of this type is between 28 and 30 centimeters long? Let's see, the center is at 25, so that would be a plausible result to get. They're asking us to find the probability that X is between 28 and 30 centimeters. So if we put a graph on this, here's how it would go. These are usually pretty low effort graphs. They don't have to be fancy at all, like we mentioned before. On our axis, we have X, and this is going to be in centimeters for that bone length. Next, we can put 25 here, and here's the organizing information. We're going from 28 to 30 on the graph. Let's see, 28, probably around here. And 30 is less accurate, but that's okay. We'll just use this to organize information. So whatever the probability is, it's going to be represented by that area right there. That's our answer, but it's really hard to calculate that area from a drawing. So we'll use, in the normal CDF calculator, that'll be input 1, 2, 3, and 4. So let's get this calculated and see what it comes out as. To start out, hit second bars to get us going. Normal CDF to get the areas. Now our lower is going to be 28, right where the area is fenced off on the lower bound. Upper bound is 30, and mean goes 25. Standard deviation at 2. So our calculator should look about like that. In some people's calculators, you have to comma separate these values. And if you have one of those calculators and you'd like to see it on that version, please let me know after I get this number. I can put up a calculator that does have that comma separated input. But really, in that calculator, here is how it would look. After you click on the paste, it just puts it in. You get normal CDF. Oh, let me fix that. Your first input would be 28 for lower. Second input is 30 for the upper. Then the 25 right here is your third input, and your 2 right here is your fourth input. It's kind of weird, but even if your calculator says TID4, you may not get that screen that we've been showing. It probably just comes in like this, and you have to insert your commas. Then, either way we do it, I've got a 0.0606 after rounding. Our projector is really working hard today. And how's that look to folks? Are people getting about that quantity there? Okay, sounds like we're in good shape. And so it looks like we're not sure what kind of deer, we're not sure what kind of bone this is. Looks like a totally made up problem, and I'm certain it is. But there's about a 6% chance that the length in centimeters is between 28 and 30. You don't have to give that practical interpretation, however, unless it specifically asks you to. And the hint that it's probably going to ask you to is if the question looks like this instead. Well, any questions so far, folks, on our part A? Okay, that's another normal distribution down. Now, the nice thing about statistics is it is a pretty tough subject, if we're being completely honest. But a lot of these problems are so common that we just do them repeatedly. And doing this kind of work, it should start to feel pretty almost second nature at this point. We've done loads of these kinds of computations. This one is definitely different, but if we're used to putting everything together in a graph, this one's not too bad either. We'll start with probability, X bigger than 26. We're going to make it our own. We'll leave the equal there blank and come over to the right to do the work on finding the value. Just by organizing information going inside the calculator. So here's X again in centimeters, 25 in the center. And we want to know the probability that X exceeds 26. Now at 2 centimeters, that's 1 standard deviation, which would be about here. So it looks like this one's not that hard to place. It would be right around here, 26. And this definitely gets tricky at this point. which direction would we shade the area? Should we shade to the right or should we shade to the left? I agree, we should all be going to the right. This is saying greater than, so we're on the right-hand side here. I think this is probably the easiest way to get a little bit mixed up on exam, since those kind of concepts, even if we're super familiar, a slight stress on the exam can just make these slightly foggy. So if you see this direction, it's just saying shade to the right. So let's do that shading. There it is. And then this implies when we go to put information in the calculator, 26 is input 1. That's going to be the lower. That's where the area starts. For our upper value 2, we're going to use positive 1099. And same last two inputs. Does this look all right to folks so far with that organization? Okay, let's throw it back into the calculator. TI-84 is definitely working hard today. So second vars, back to normal CDF, and we're not changing a lot. Lower is changing to 26. For upper, put 10 power 99, and then just lots of enters. Oh, that was too many. That comes out as a 0.3085. Looking at this graph, I'd say that's plausible. If I were to have guessed, I probably would have said 40%, but I'm going to trust the calculator on this one and not my not great by hand sketch. These pictures are only meant to organize information. I try to put that value of 26 about where it would be, but it doesn't ever have to be placed perfectly. So even if the area doesn't look right, but you know you put it in the calculator right, this is still what I would consider a correct graph. It does not by any means have to be perfect. Well, this time we do have to give a practical interpretation. These are never too bad. We've done a lot of practice on these kinds of things. We can focus on this first and say, there is a 30.85% chance that, now we switch gears and we have to talk about X. Anyone recall what X represented? Kind of foggy myself. Yeah, exactly. We'll say pretty much just that statement. There's a 30.85% chance that a randomly selected, this came from a deer, so randomly selected deer has, well, they told us a specific bone, but they never said what type of bone. So I'll just say a bone of this type has a bone of this type. Oh, and again, we can also just read it off from up here. Of this type that is, here we'll just say verbatim, greater than 26 centimeters. Greater than 26 centimeters. So that's our practical interpretation on that one. Does that look right to folks on this conclusion here? Okay, it's kind of a strange problem because the context is not very filled out, but it definitely feels like it's just a random problem that was made up by ChatGPT or something like that. But it's a pretty decent one for the sake of practice. So let's try out the next part. Part C is saying, what length describes the 10% of deer that have the shortest bone of this type? And once we find it, we'll round to 2 decimal places this time. And this is pretty common. Usually our probabilities we keep to 4 places. And if we're finding a value on the x-axis, we'll round differently, maybe to the wholest integer, to 1 decimal place. Here we're doing 2 decimal places. So first thing we ought to do is, let's write down a probability function that goes with it. We want to find the probability that it says 10% of deer. Well, already that 10% is a big hint. If they give us a probability, it's going to go right here. We can't put in 10%. We really ought to put 0.10 this time because the percentage will not go into the calculator correctly. That would give us an automatic syntax error. Well, that's the probability statement so far, but we know X is involved. That's going to be the length of the bone of that particular deer. Now we have an unknown value K that should go here. And the last thing we need to decide is, what should this be? Should this be a less than sign going like that? Or a greater than sign going like that? Yeah, absolutely. Thanks for spotting that. Right here in the context is the final part where it's going to give us a definite direction. This is kind of like the problem where we're talking about snowfall in Rochester, New York, and we were wondering about 1% worst cases. Here, this is being specific. It's just saying shortest is what we mean directly. So let's put a less than here. That's finally the full probability statement. And our whole goal now is we want to solve for K. So back to another normal distribution. Takes just a moment to fill this out. Okay, with that in play, next thing we have to decide is, well, where should K go? It's saying area to the left of K this time needs to come out as a 0.10. So I'd be placing it right around here somewhere. Does that make sense to everyone? Awesome. Let's drop our K right around here. So now we have shading going in this region. And the very common calculator, the one that we've been using in class all along, only accepts area to the left. That's good for us because we have an area equals 0.10 right exactly here. If our area was on the right-hand side, we use a trick of 1 minus whatever it is to get the left-hand area. So this turns out to be enough organization. We're going to be using inverse norm only because of the probability given. And in the inverse norm, input 1 is area. And last inputs are just the same as before. So let's throw this all into the calculator and see what K comes out as. Definitely double check it, and on the graph as well. It's easy to kind of flip which side K should have been on, the left tail or the right tail for this problem, but you'll know right away once you check in the calculator. So let's take a look. We're back to second bars. Now inverse norm, you'll know you're in the right place because it's accepting that probability, which is an area, so 0.10. But it's not always 0.10 that goes in. It depends on the graph. Sometimes it might be 0.90 instead. But last two inputs are 25, 2 for mu and sigma respectively. And that's our value to 2 decimal places. It's 22.44 centimeters. Well, let's not accept it right away. Let's take a look. 22.44 centimeters, that does fit this picture. It's substantially left of 25. So I would say it's plausible. Let's go with, I already forgot the number. Let me try again. 22.44 centimeters. So we did it, folks. This is solving a very, very bizarre looking equation. What the calculator did was just invert what the probability was doing and gave us this correct K value. Any questions so far, folks, on that one? Okay, well, it looks like we have one more to go and about 6 minutes. I think we'll make it. Oh, this is the longer one too, but let's see where we end up on it. Here, we're solving probability X is greater than K, so the inverse of this situation. And we want it to be at 0.02, so we're looking at 2%. I'll start just by copying that in so we have it available. Oh dear, let me fix that color. Then back to another normal curve. What's weird is these seem like they're easier to draw the bigger hurry you're in. When you're just not careful, the curve comes out a little bit better. Okay, so we've got it so far. Now where it says probability X bigger than K, oh, forgot the probability, let's throw that in, is 0.02. What we're saying here is area to the right of K is 0.02. That means K this time has to be on the very far right upper tail, somewhere in this location. And we put here area of, actually let me shade in a better way so we can actually see that. We'll put to the right over here an area of 0.02. And that's a big problem in the calculator. It won't accept this value. And if you try to give it, it's going to give you a number way over here on the wrong end. So this is one of those situations where we'll go and put in 1 minus 0.02 equals 0.98 is what goes right exactly here. So our calculator is only going to accept the left tail area. We'll give it 0.98. Double check we have a K value exceeding 25, and then we'll be in great shape. Any questions so far, folks, to that stage? Okay, let's put it in. So second vars, once again, option 3. Area, we'll put in 0.98. Mean is 25, standard deviation is 2. And so with all that thrown into the calculator, this one to 2 decimal places becomes 29.11 centimeters. 29.11. Does that look right to folks to that stage? Awesome. Well, last thing we have to do is give this thing a practical interpretation. Any volunteers for how we would interpret 29.11? Yeah, go ahead.
There's the two points that the following is type of years greater than years.
Yep, that's exactly what I would say on this one as well. So that's our interpretation. If it feels like this is not too bad to get through, then you're in great shape for the class. Really, all we did was we looked right here, came from the percentage, the bone length of this particular type of deer, that's just referring to X. And then we just literally said it's greater than the value we found right over here. So that's how those interpretations all go. Same for confidence intervals. They're all highly, highly similar. Well, any last questions, folks, on this document so far? Okay, well, I noticed I thought for some reason there wasn't as many problems, but there's another problem on here. I don't think we can solve it in 2 minutes, but it might be an interesting one for the sake of studying on exams. This one is about, it says here, 2/3 of people have a dominant right eye or foot. They want to know if there's a dominant side for kissing, if you lean more to the right or left as a couple. So that might be an interesting problem on its own. I'll definitely solve that one in case you're curious about it or just want an extra resource for studying. So the full solutions will be posted. Any other questions so far, folks, before we call it a night? Okay, well, have a great night, everyone. If you're studying over the weekend, you can definitely use the Ask My Teacher button, send me emails, that kind of stuff, request extensions. I'll still be available and happy to help out. Have a great night, folks, and I'll see you all on Monday. Hey, question?
For some reason, my calculator isn't working on this last one.
Oh dear. So this was getting
Sorry,
the,
can I have the test back
Oh,
quickly?
yeah,
I just
absolutely.
realized an accident I did.
I just stole it from you, sorry.
Sorry.
No worries. So how did you get the information in?
Bars, normal CDF.
Oh, but you would want to use inverse norm on this one.
Really?
Yeah, if you're given a probability like this right here, you're always doing an inverse norm.
So we just ignore the upper, even though we have it. Is that
Well,
what the problem is?
We don't ignore the upper, but we have to use the lower probability of 0.98. Oh dear. Yeah, it put inverse norm in as the lower. But to get out of here, you could hit like second and then quit. Huh, maybe second quit again?
Oh, I hit the wrong button. There you go.
Oh, I see. I was pointing at the wrong one.
Okay,
Yeah, so this one is gonna be for inverse norm.
there we go.
Yeah, the area we have to give is the left tail area. And yeah, you've got it. That's the
Okay.
right figure. And if you made a mistake, I do this all the time and put in 0.02. Your K won't look right, but
Well,
that's
I
just
was
your,
getting a 0. I'm like.
oh, yeah, I see.
I'm like, I know something's wrong. Okay.
Mhm.
I thought we used inverse norm, but I think because my
I
brain
gave like
is,
two values,
my
so
brain is on null hypothesis too much right
yeah,
now.
yeah, I
Okay.
agree on that.
Thank you.
You betcha.
Yeah, I'm so sorry.
Oh, no worries at all.
I just keep, for some reason, randomly mixing the successes and failures for the normal
Yeah.
distribution compared to this one.
Mm,
It's really weird.
yeah, no worries at all.
I kind of should talk about that one web assignment problem that's been bothering me
Mhm.
for that one chapter, but I think I'll just talk to that with email.
Okay, that'll work for sure.
I hope you have a good weekend.
Thanks, you too.